Okay, so today we're going to do worksheet 4A. We're going to use a lab scope for the first time. So there's a few questions on here that you're going to have to answer at the top. Some of this we spoke of in theory. Okay, below that there is a grid which represents the screen of the scope and the pattern that we get for our initial pattern that we're going to look at. We're going to look at a fuel injector first. You're going to draw the pattern on here. I want you to put the time base and the voltage scale that we have set on the scope on the picture here. And then I'm going to change the time base and you're going to see how the pattern changes. You're going to put that down in here as well. Okay, the other side of the sheet, we're going to look at current. So the first side is voltage, this side will be current, and basically you're going to repeat the same process with current instead of voltage, which we're doing for the front side. So the first thing that we are going to do whenever we work with any kind of electrical circuit is we're going to highlight our wiring diagram. So we have our wiring diagram here, and now this goes to another diagram on the in the wiring diagram section. I know we have ignition fed voltage to this point. I'm not going to get the power distribution diagram. So simply on this diagram we're going to go ignition feed, which of course will be orange. Anytime we're doing switch power, we always do orange. So we're going to go orange into the circuit, and then we're going to come down to this splice. Okay, now from this splice it goes to various other components. We have our idle speed control actuator, our CVVT oil control valve, or our variable valve timing control valve. We have a purge solenoid over here. We're not going to worry about those components. We're simply going to do our fuel injector circuit right now. So from this point, this car is a little bit odd in the fact that number one fuel injector receives voltage on a separate wire from the other two. Now it comes in the same place, and the same fuse feeds both sides of the circuit, but our three injectors all branch off of this wire, and for number one injector it continues straight through. So number one injector will have a separate voltage input from the other three injectors. Okay, and now we need to look at our control side of our circuit. These injectors are ground side switched, so the PCM is controlling ground of each injector. So these are switch ground, which we represent with green. So very simple diagram to highlight in this case. And I know it looks like a parallel circuit, looking at it the way it is. However, each injector is controlled separately, which makes each injector actually in series, not parallel in this circuit. Okay, so that is enough of our wiring diagram. So what I'm going to do first, we're going to look at injector 1. Okay, so we're going to look at the voltage pattern from this injector. So in order for me to get the voltage pattern I'm looking for, I'm going to back probe here at terminal 2 of injector 1, which is going to give me the control of the injector. If I was to back probe on the power side, all I would see is reference or source voltage. Okay, this is going to be source voltage from the ignition switch. So all I would see running with this vehicle, which is what we're going to have it, would be 13.9 or 14 volts, whatever charging voltage happens to be for this particular vehicle. When I back probe the control side, however, I will see the PCM turning this on and off, and we will get our injector pattern from it. So we're going to do that right now. I'm going to put this down and we'll get our test leads out. Alright, so the first thing that we're going to do is we're going to use our test leads here, and first I'll show you how I'm connecting it to the injector, and then I will show you how we're going to set the scope up for it. So let me get this out of our way. Alright, so we have on our test leads a back probe. That's to go into the injector harness, and then the other side, of course, we're going to battery negative or ground. So I'm just going to come in over here to the vehicle. We're going to ground our negative lead to the battery negative terminal, and then I've got a light here. I'm just going to shine this down so we can see, and I'm going to back probe the green wire of our injector. That is the control side of our injector. Okay, so that is back probed, and my battery is connected. Now that back probe connection I may have to adjust once we see if we have a pattern on our screen. So we'll leave our test light over here. I don't need that. Okay, so over here we have our scope. So we're using a Pico scope. So this is a PC-based scope. You can see the cable, and that goes into the USB port on the computer. The program, of course, is in the PCM. You download that from Pico. Now this scope is not exactly an automotive scope. It's a general scope, but we can use it for automotive purposes if we know how to use a scope and what the settings should be. And one of the main things we need to be worried about with this scope is 20 volts peak max input to this scope. Now the automotive version of this is 100 volts. So it's a little bit different. Plus the automotive version software will have automotive related presets that this software does not. But like I said, that doesn't matter if you are an experienced scope user and you know what you're connecting into and what you should expect to see. So being that that is a low voltage input, in order to protect the scope, when we know with the fuel injector, when that magnetic field collapses in the coil, we have a high inductive kick. So we're going to use this device. This is called an attenuator, and basically this is a resistor that goes in series with our injector, so that high voltage spike does not damage the scope. So this is going to filter it basically 20 to 1. So if I have 100 volts coming into this, divide that by 20, I'll have 5 volts actual voltage coming into my scope, so it's not going to cause any damage. So that's going to go here. We're going to put that on channel 1 or channel A, and then I connect my BNC cable, which is going to my sensor, to that. Okay, so that is all set, and now what I need to do is set my scope screen up for it. So my scope screen is here. We're on channel A. Okay, so channel A right now is set for 10 volts to 100 volts. So we'll start right there. That's a pretty good base setting for this. Okay, and then I need to set my time base. So my time base here is in nanoseconds at the moment. I'm going to set this to, we're going to start with 20 milliseconds to begin with. 20 milliseconds is a good general starting place usually for this style of pattern. And we can see the blue line across the scope. I'm just going to bring this up a little bit higher. So that is where the trace will occur when I start this vehicle. Okay, so I'm just going to go and start the vehicle, and we can see what we get on the screen. Okay, so we have a pattern on the screen, but as we can see, it is very unstable. It's moving side to side. So in theory class, we talked about setting a trigger, and this is why we need to set a trigger. So the trigger is going to capture this waveform on the screen in a position that I want it to be. So at the bottom of the screen here, we have trigger. Okay, so I have trigger there. If I connect, you see how here it says none. So I'm going to click on this, and I'm going to go to auto. And now you can see that my pattern is up on the screen. This diamond here is the actual trigger point, and I can move this around the screen and put my pattern where I want it to be. Okay, so if I want it over here, that's where it's going to be, and you can see how it is in line with it. Okay, so that is what I'm looking for. This is a typical fuel injector pattern for a saturated switch type fuel injector. So the pattern's very, very small. I'm going to make this a little bit wider, and the way I'm going to do that is to actually decrease the time base. Okay, so if I go onto a smaller time base, we can see here we're down to 5 milliseconds now. You can see how that's affected the pattern on the screen. It's actually made it wider. So in the bottom box on your lab sheet, this is what we're going to do. As I decrease my time base, I increase the size of the pattern on the screen. Of course, if I go the opposite direction, it's going to do the opposite effect. Now I'm going to make it very, very small. In fact, I have such an increased time base that I can see the same pattern repeat. This is number 1 injector, so between each one of these patterns, we know we have 720 degrees of crankshaft rotation. So I'm going to back this back out because there's a few important things we need to talk about related to this particular diagram. Alright, so we're going to go with this one right here. And some important things that we need to look at when we're looking at a fuel injector diagram. So at this point right here where we see this voltage drop, this is actually the PCM turning this injector on. So we have source voltage up until this point. You can see on the side here we're at 13.919 volts, and then the PCM takes it to ground, and the PCM will hold it at ground and then release it. So from this point to this point is actually the pulse width of our fuel injector. That is the amount of time that the PCM is commanding this injector on. And the PCM commands this injector by controlling the ground side of it. When we turn the injector off, we have our inductive voltage spike, which is a byproduct of turning off a magnetic field. This is not really desired in this case. It's a byproduct of the type of component it is. However, it does give us an indication of the strength of the magnetic field. If I have a good high inductive kick, that gives me a good indication that my magnetic field was nice and strong, and the coil or the windings in my coil are all in good condition. I don't have a shorted winding anywhere. Now if we look at the turn off of our injector, there's a little bump right there that we can see. Okay, that is extremely important. This little bump represents the pintle in the injector physically moving. It's closing right now, which means it's actually able to move. If I test a fuel injector, let's say I have a vehicle with a misfire, and I assume that I think that possibly there's a problem with the fuel injector. If I don't see this hump, well, I found my problem. This injector is stuck physically closed. Okay, and that's going to cause my misfire. Obviously, I'm going to have no fuel being sprayed out of the injector. Now, when we look at current in a few moments, we'll see the actual injector opening event in the current waveform. So when we look at the two of them together, we can actually see the physical movement of the injector. So in this case, we are looking right here, and if I spread this out a little bit more by changing my time base again, okay, it's actually more pronounced now. We can see that pump right there, and that is where our injector physically is closing. Okay, so that is worksheet, the front side of worksheet A. So now what I'm going to do is end this video here, and we will come back with the second video where we'll look at amperage for the same component.